beta distributions. But you know what? I actually received some messages from some of you, and I actually want to have a review on the exponential Weibull, okay, then gamma and beta distribution. I'm going to tell you the connections they have. So because of that, I edited the lecture slide that I uploaded previously. I wanted to go back to the course module. I've already edited that. Okay, so we started continuous probability distribution. So in the outline today, I'm actually going to have a recap on the exponential and the Weibull distribution. Then from there, I'm going to talk about gamma distribution. Then lastly, I'm going to talk about the beta distribution. Now, I told you something the other time. We find ourselves in a probabilistic world. And if we really want to understand this world, excuse me, you need to be probabilistic inclined. We need to identify the appropriate probability distribution of the state of nature. Now, in terms of, we have two types of random variable. We got a discrete type. We got a continuous type. Previously, I've already, I told you, we have some probability distribution under the discrete type that I've walked you through, like binomial, negative binomial, pagiometric, and so on like that. But we also have the probability distribution of the continuous type. Of course, I've walked you through normal distribution, the exponential distribution, and the Weibull distribution. And of course, today the focus is going to be on the gamma and the beta distribution. But you know what? I quickly want to have a recap on the exponential and the Weibull distribution we've done before, and how can we actually distinguish between exponential and the Weibull distribution. And that is the reason why I'm having a recap right now. Now, let me tell you this. Do you know that you can save yourself computational time when you attend the lab? On average, if a question is going to take you like 3 minutes to compute manually, using the lab, it may take 1 second. And what I want to show you today is I'm going to start from the exponential distribution. How can you actually compute the exponential distribution if you are using an R software? Because that is what you learn in the lab, right? And let me first tell you, what is the meaning of the exponential distribution? The exponential distribution is actually used to model the waiting time before the occurrence of an event. But one thing with the exponential distribution, the exponential distribution assumes a constant failure rate across time. Constant failure rate. Exponential distribution has what I call a memoryless property. It doesn't matter if you're waiting for the occurrence of an event. It doesn't really matter how long you've waited. The distribution is going to be the same. And you know what? It means exponential distribution is not appropriate to some situations whereby the failure rate is not constant over time, because there are some situations where in survival analysis or in the reliability study where the failure rate is not constant over time. Failure rate, we could have a situation where failure rate increases over time or failure rate decreases over time. Therefore, we need a we need a distribution that have a memory property. Exponential distribution is memoryless. It doesn't take the probability, okay? It doesn't consider where the state you are in. It doesn't consider, where you started from. is assuming the probability distribution is actually going to be the same all through. And that is not realistic when you look at some practical situations. Now, let me take a look at this. The exponential distribution, we have f of s equal lambda exponential s power minus lambda s. The lambda is the rate. Okay. And if they want to ask a question about exponential distribution, the question could be one of these. Find the probability of x less than 1, or find the probability of x greater, or find the probability of x lie in between. I remember the other time, if you want to do that manually, before of us get a CDF, you know, we got a CDF, right? The CDF that we actually got, you know, when x follow exponential distribution with a parameter lambda, those of you online, can you see what I'm writing on the board? Can you confirm that? If you're seeing what I'm writing on the board.
Yep.
Thank you so much. Now the f of x is actually lambda exponential raised to power minus s, s greater or equal to 0, lambda greater than 0. And of course, if you want to find the CDF, I showed you the probability of x less or equal to that is actually 1 minus exponential lambda x. This is the CDF. Okay. Now, if you want to solve this problem, the probability of x less than 1, you're going to plug in 1 for x, and your lambda here is given to be 2. Of course, that is how you're going to do that manually. But if you want to use R, very easy. If you want to use R, you're going to write PESP. PESP. You only need to indicate what is your x and what is your lambda. In this case, x equal to 1, lambda equal to 2. Automatically, it's going to compute that for you. Your answer is going to be 0.8647. When you use that for me in exam, that is highly acceptable. Okay, that is highly acceptable. And if you want to go manual way, there's no problem. But what I'm just trying to tell you is that, of course, you're actually going to get your result on time when you make use of a software. Okay, what if you want to solve a problem that has to do with a conditional probability with the exponential? You want to find the probability of s less than 6, given that s is greater than 5. You remember the way we do conditional probability. If you want to do this manually, you need to first look at the intersection between x less than 6 and s greater than 5. You find the probability of that divided by the probability of s greater than 5. If you want to do that in R, or what you're just going to do, you need to identify what is your parameter. The parameter is 2, lambda equal to 2. You're going to plug in that. You plug in 6. Now, when you plug in 6, what you are trying to do here, you're subtracting when you plug in 5 and when you plug in 6. Okay, then divided. What is the probability of s greater than 5? The probability of s greater than 5 is to do 1 minus the CDF. But if you want to do that in R, it's going to be 1 minus PESP 5,2. Easy way you're actually going to get your result. Look at that. If you take a look at this, you are getting this result. You're getting the same result, right? This confirms the memoryless property of an exponential distribution. So what I just show you now is how to compute exponential probability with a software R. Okay, that is how to go about that. Now, what about Weibull? You know, if you want to do Weibull distribution, if x follow Weibull distribution, of course, x follows Weibull with parameter alpha beta, f of x equal alpha over beta raised to power that alpha minus 1 exponential raised to power this raised to power alpha, alpha greater than 0, beta greater than 0, s greater than 0. Now, this is actually the PDF of a Weibull distribution. Let me tell you this. The parameters in Weibull distribution, we call one shape parameter, we call the other one scale. This guy here, alpha, is a shape parameter. And of course, the shape parameter is that is what give that is what determine the shape of the distribution. And we have beta is a scale, and the scale parameter is just going to tell us how the distribution spread out, And you know what? In you know, when alpha equal to 1, okay, when alpha equal to 1 and beta, okay, and beta equal 1 over lambda, the Weibull distribution becomes an exponential distribution. And let me tell you this, the difference between the Weibull and the exponential distribution said there's a constant rate over time, but the Weibull distribution, said no constant rate over time. When alpha is greater than 1, it means the failure rate increases with time. Okay, the failure rate increases with time. When you look at it, when I want to use the COVID cases, you're going to see those who are aged, like the elderly one, they are more prone to getting COVID compared to the youth. Okay, in that situation, you're trying to say the failure rate or the hazard rate actually increases with age. Okay, the exponential distribution cannot be used in that kind of situation. But what we're going to use is Weibull distribution. So Weibull will allow, whether the failure rate to be, to increase over time or decrease over time, depending on the values of alpha, the shape parameter. Okay, if alpha is greater than 1, it said the failure rate will increase over time. If alpha is less than 1, then it said the failure rate decreases over time. Okay, I just wanted to see that. Now, suppose that the time is days to development of a tumor of rats exposed to a carcinogen is well approximated by Weibull distribution. With A equal to 2 and B equal to 30, take a look at this. At time I can use A and B, I can use alpha and beta. Okay, the A and B here indicate the parameters. Okay, I can use alpha and beta, we can use A and B, okay? Now graph the density of the CDF and the survival curve for this random variable. Okay, and they want you to use for the range of first, it's going to be from 0 to 80. From 0 to 80. So maybe, we're talking about the age, we're talking about the time is there to development of a tumor. Okay, now I want to show you this. If you want to do this in R, it's going to be curve D S shape equal to 2. You have been given your shape, your alpha or A, that is the shape parameter equal to 2, the scale parameter equal to 30. You are always going to be given that. But let me tell you, in real life practical situation, you are not going to be given that. You're going to be the one that will estimate that. We normally estimate that from the data set, but that is beyond the scope of this class. If you come back for upper level course in statistics, of course, you're going to learn how to estimate the parameters of a distribution. But for now, you're going to be given, okay? Does that make sense? They will give you the shape parameter. They're going to give you the scale. Now, take a look at this now. You see the density, it is skewed to the right, indicating that the Weibull distribution is not normally, this is not a double bear shape, it's skewed. And of course, if you want to model reliability data, survival data, you cannot assume normality. Okay, this is an evidence. Now, if you want to get a CDF, this is going to be the shape. It's just going to be P Weibull. Then you write all that. Okay, this is the shape of the CDF. And of course, if you want to look at the survivor, when the CDF is in survivor analysis, the CDF is more or less like a failure. What is the probability of something less or equal to? Why the survivor is going to be greater than that? So this is how do I compute the survivor? It's going to be 1 minus the CDF. Look at that. I got this. This is a survivor proportion now. Take a look at that. Now, how do we use R to answer a question, to answer a probability question regarding the variable distribution? Take a look at this. You already given the shape parameter, you given the scale parameter, and they ask you to find what is the chance that the rat will be tumor-free for more than 40 days. It's going to be tumor-free for more than 40 days. There's something in survival analysis that we call remission, which we're talking about the time, the symptoms will disappear. But that doesn't mean it cannot still reappear. That's because we could talk about the recurrence, okay? But right now, if you want to do this, instead of you to go through the rigorous mathematical way, because they say more than 40, right? More than 40, it means you want to find the probability of S greater than 40 using Weibull. Now take a look at this. For Weibull distribution, the probability of S less or equal to S is 1 minus exponential raised to power this, everything raised to power alpha. This is the now what you want to find now, the probability of S greater than 40, which is going to be 1 minus this. Okay, and this, you're going to use this, where you're going to plug in your S is going to be 40. And of course, you are giving your alpha and beta. But you know what? Instead of wasting that time, if you want to use the R software, oh my God, you're just going to do 1 minus P Weibull, 40. Then you indicate your shape and the scale within 1 second. You're going to have your results. 1 second. But I promise you, if you want to work that manually, it may take you like 3 minutes. And there's possibility you could get it wrong when you don't, when you miscalculate. So that is the result. Now I'm going to show you something more. What if I want to find a probability? What if you're giving S follow a Weibull with parameter A equal to 1.2, B equal to 0.5. I told you I can give you in A and B, or alpha and beta, they made the same. Now you want to find the probability of X less than 1. Instead of you to make use of the formula here, you can just do P Weibull. Look at that, P Weibull. P Weibull indicate the number 1, indicate the values of the two parameter. Automatically the result is going to be given 0.8995. Let me tell you this, R software is the simplest software anywhere in the world. You don't need to be an expert in software to understand how. You can download R today, before you know, you're going to be experts in it. Very easy. Okay. Now, if you want to find the probability of S less than 6, given that S is greater than 5, with Weibull, okay, it's going to be P Weibull minus another P Weibull. That is when it is 6 and when it is 5, divided by greater than 5 is 1 minus P Weibull. Easy. You're going to get your result. Easy. Look at that. Now, you remember when I was working with this the other time under exponential? You remember I got the same result. I'm going to walk you back. I want you to say something. When I was doing that, look at that. With the exponential, using the same thing, what did I get? The same result. That indicates memory less property, right? But when I did the same with Weibull, what happened? Different results. Weibull has memory. That is what it means. What Weibull is talking about is that the failure rate is not going to be constant over time. It has a memory. It means the probability of the current state of events actually depend on the numbers of time elapsed. That is what it means. You got a different result here. And this is the reason, one of the reasons why Weibull is highly preferred by researchers compared to the exponential distribution. Take a look at that. Okay. And I put a takeaway here. I said, when A equal to 1, that is when the shape parameter equal to 1, where A is the same thing as alpha, then the Weibull distribution actually reduced to exponential. And of course, when you have exponential, then you have a memory-less property. Of course, when you have a Weibull distribution, you have a memory property. Okay, now when A is greater than 1, it has an implication. When the shape parameter is greater than 1, you're trying to say the risk of failure increases as time goes on. When it is less than 1, it decreases as time goes on. So that is the difference between the exponential and the Weibull. Is there anyone who want to ask question on the difference between exponential and Weibull before I go to new distribution called gamma? Is there anyone? Okay, you guys are good, right? Those of you online, you can you confirm if you're hearing me clearly?
I can hear you.
Okay, thank you so much. Those of you that will be joining online, there's no password. The moment you click on the link, is automatically you're gonna let you in. No password. Okay, to get in. Now I want to get into what I call a gamma distribution. A gamma distribution is another distribution from, it's also very useful in survival analysis and in reliability engineering. It's also a very good distribution for modeling, the waiting time before the occurrence of a certain event. But let me tell you this, it also has a lot of application, service time modeling, the Q theory, and so on, like that. And let me also tell you this, gamma distribution is another generalization of an exponential distribution. I want to tell you particularly in real life, we use gamma distribution to model the size of insurance claims, the size of insurance claims, and the amount of rainfall, particularly the cumulative amount of rainfall, okay, can actually be modeled by gamma distribution. So those are the real life practical application. Okay, I want to show you the structure of the gamma distribution right now, but I, for us, want to start with a gamma function. There's a difference between a gamma function and a gamma distribution. I wanted to take a look at this guy, gamma alpha. Okay, that guy there means gamma alpha, or gamma alpha equal to integral 0 to infinity, x raised to power alpha minus 1 exponential raised to power minus LDS. That's a gamma, that's an integral definition of a gamma function. And let me tell you this, when you now want to have a gamma distribution, this is the formula. Okay, it is f of s equal 1 over beta raised to power alpha, gamma alpha exponential raised to power alpha minus 1, x raised to power alpha minus 1 exponential raised to power minus x over beta. Okay, when you take a look at that, that is a probability density function, okay, for gamma. And we also have two parameters, just like the two parameters we have in Weibull. Okay, we have so many alternative distribution for modeling, waiting time. It is not only exponential, not only Weibull, but also gamma. Okay, the two parameters here is alpha, beta. Alpha is the shape and beta is the scale, just like what we have in the Weibull distribution. Now, when you take a look at this, the mean is alpha, beta. The mean of the expected value of x in the gamma distribution, it is a product of the two parameters. And of course, the variance is alpha beta squared. The variance is alpha beta squared. Okay, the mean is the product of the two parameters. Okay, I'm going to write that. So when we have a gamma distribution, okay, when you have a gamma distribution, okay, the mean E of x is alpha beta. Okay, the variance of x is alpha beta squared. So this is when x follow gamma, okay, with parameter alpha beta. And of course, I write the f of x equal alpha raised to the power of this, gamma alpha x raised to the power of this, exponential raised to the power of that, x greater than 0, alpha greater than 0, beta greater than 0. Okay, so take a look at that. So that is the gamma distribution. Okay, now when alpha equal to 1, okay, when you take a look at that, when I plug in 1 here, it's going to give me exponential distribution. I just wanted to take note of that. Okay, exponential distribution is a special form of a gamma distribution. And of course, if you want to have the exponential that we have in class, well, lambda is going to be equal to 1 over beta. Of course, when you put lambda to be 1 over beta, you are automatically going to have f of s equal to lambda exponential raised to the power minus lambda x. Okay. Now, how do we solve problem with gamma distribution? How do we actually solve problem with gamma distribution? Suppose x equal to time between failure, time between the occurrence of an event. Okay, like I said, I'm going to tell you under the continuous type distribution, whether it is normal, gamma, exponential, because when you look at exponential, gamma, Weibull, they are all distribution for modeling waiting time before the occurrence of an event. And that is the reason why in exam, I'm actually going to tell you the particular distribution I'm talking about. Okay, suppose s equal to time between failure is known to be modeled by a gamma distribution with a mean of 8 years and a standard deviation of 4 years. Calculate the probability of failure before 5 years. The probability of failure before 5 years. Now, what are you going to do? You need alpha and beta in this situation. You know, you're not giving parameter, but you are giving the mean and variance. And you know that the mean is alpha beta, the variance is alpha beta squared. The mean given is actually 8 years. You're going to say this equal to 8. What is the variance given? Oh, they give you the standard deviation of 4 years. Then the variance is going to be square of standard deviation, right? That will be 16. Now you solve this equation simultaneously to be able to obtain your alpha and beta. You solve this equation simultaneously, and when you solve it, I got alpha to be equal to 4 and beta to be equal to 2, because you need the parameters if you want to answer a probability question about any particular distribution. Okay, now you were given mean and variance, and you are able to find your alpha and beta by solving the two equations simultaneously. Now, do you know that if you want to achieve this thing out, you know what you're going to do? You want to find the probability. You actually want to find the probability of what? The probability of, it said calculate the probability of failure before 5 years. It's just the probability of s less or equal to 5. If you want to find before 5 years, less than 5, we know whether less than 5 or less or equal to 5 is the same. We treat them the same way under continuous. If you want to use how to do this, it's just going to be P gamma. You remember when we're dealing with exponential, we use P ESP. When we're dealing with Weibull, P Weibull. But now P gamma, then I indicate that number. Then what about, then I'm going to indicate the shape. The shape equal 4 and the scale equal 2. Automatically, I'm going to have my results. You don't need, you know, when you try to go and use a formula, that is going to waste your time. Okay, because if you want to use the formula, if you want to go manually, this is what you're actually going to do. If you want to go manually, f of x equal alpha, this gamma alpha, x raised to the power this exponential raised to the power that. Okay, if you want to find the probability of x less than 5 is going to be 0 to 5. you plug in your alpha and beta, which is going to be 2, which is going to be 4, 2 raised to the power 4 gamma 4 x raised to the power 4 minus 1 exponential x raised 2 dx. If you want to do that manually, this is what you're going to do. And when you take a look at this guy here, gamma 4 is 4 minus 1 factorial, which is 3 factorial, right? 6. So here you can bring this guy out 4 over I think that is 16 3 factorial 0 to 5 x raised to the power 3 exponential x raised to the power 2 dx. You need to integrate that. This is going to take forever. It's going to waste your time. Why not using P gamma, indicate the number, the shape, that within 1 second you have your result? But it's a matter of choice. I'm not imposing this on you. You can actually decide if you want to go manual. There's no problem. You get what I mean? Okay. So that is what I was trying to, to do here. This is another question. Okay. And then, I also wanted to take note. Okay, now take a look at this. Look at that. The probability, if for gamma, if they say, what is the probability of x less than 1? Giving your alpha equal to 2, beta equal to 0.5, what did I say you're going to do? P gamma 1, shape, scale, lower dot A equal to 2. Oh my God. Within 1 second, you have your result. P gamma will solve the probability of something less. If they ask about something greater, that will be 1 minus that. Okay? Now take a look at the something greater here. Something greater, what happened? 1 minus that. As easy as that. Okay? Now you're just going to have your result. Another way, if you don't want to do 1 minus that for greater than 1, okay, you're just going to write 1 shape equal to that. Under the lower dot A, you're going to say equal to false. Under here, you are saying equal to true, right? That's another alternative way. How do you find between this and between this? Okay, that will be, you find the probability of S less than the upper part minus the probability of S less than the lower part, which is going to be P gamma minus P gamma. Take a look at this question now. S follow gamma distribution, and let's lie between 1 and 2. Okay, given that the alpha equal to 2, the beta equal to 0.5, what are you going to do? You're going to write P gamma, use the upper part 2, indicate the shape, blah, blah, minus P gamma. When you put a 1, oh my God, within 1 second, you have your result. Within once, if you copy this into R today, you're going to see that easy. Within 1 second, you're actually going to have your result. Okay? Now, that's all about gamma distribution. You have anybody who have question? On the gamma distribution, they could ask you to find the probability of a random variable less than or greater than or between. Now, the last distribution of the day, because today, okay, go ahead. Oh, okay. You're talking about the lower tier part of the code, right? Yeah, it's just it's just a coding part that we are actually need to put all the time. But if the lower dot A equal to is true, you are referring to the less than. If it is false, you are referring to the greater than. If you still want to maintain the true, then whatever you get, you're going to subtract from 1. But if you don't want to subtract from 1, if you want to deal with greater than, you can go direct and say the lower dot A equal to false. Does that make sense? That's a very good question. Lastly, the final distribution we want to talk about on the continuous type is beta distribution. Every distribution we've been working on, they've not been targeting proportions, percentages. When a random variable is percentage or proportions, how do we model that? Okay, then we use what we call the beta distribution. Now, the beta distribution, I'm going to show you now. This is the beta distribution. The first one that you are seeing there is called the beta function. Okay, that's an integral definition of beta function. But the one here is actually the beta distribution. You know, I'm using P and Q. I can use alpha and beta. I can use A and B. The two of them represent parameters. But what is the difference between the beta distribution and the other distributions we've done? In beta distribution, the two parameters are shape. There's no scale. Okay, the two of them. Therefore, beta, because of the fact that we have two shapes parameter, the beta distribution is more flexible than any other form of distribution we can find. And for you to be able to model a random variable within 0 and 1, you know, a random variable like proportion, like a percentage, we need more flexible probability distribution. Take a look at this. I'm just trying to show the world. When I vary the parameters, I get different shapes. Okay? It's more flexible. Take a look at that. You can, you know, the most flexible probability distribution in statistics is beta distribution. Look at that. You can have different kind of shapes. Okay, when you vary the parameter. Now, I told you this distribution is used to model something that has to do with proportions. When a random variable is proportion, or is a rate, or is a percentage, of course, you expect the random variable to be greater than 0, but less than 1, right? Okay, we're going to use beta distribution. Now, take a look at this example. The proportion of X of satisfied customers with a certain business, of course, we follow this beta distribution because when you look at your customers, some of them may be satisfied with your products or with your service, and some of them may not be satisfied. You don't expect 100% of your customer to be satisfied. It's just like the service I'm rendering now. I'm rendering the service of teaching. I don't, even if I'm a greatest of the greatest professor, I don't expect 100% of my student to be satisfied. So that is part of life. Okay, so we use beta distribution to model that. Now take a look at this. If I want to derive a probability distribution in that regard, I'm only going to plug in the two parameters. After plugging in the two parameters, and I also want to tell you, when I have B of PQ, there's there is what we call integral definition of a beta distribution, and we have the non-integral. Now the B of PQ equals 0 to 1 s raised to the power P minus 1. 1 minus s raised to the power Q minus 1 ds. So this is what we call integral definition. The non-integral definition, definition. If this is the integral definition, we also have non-integral, which is B of PQ is going to be gamma P, gamma Q divided by gamma P plus Q. Okay, so here is going to be P minus 1 factorial, Q minus 1 factorial, P plus Q minus 1 factorial. And of course, the non-integral definition equal to the integral definition. I just wanted to take note of that. Okay, if you want to answer a question, it said, it's asking you to find the probability, the proportion of S of satisfied customer with a certain business follow a beta distribution. Find the probability that the customer satisfaction is over 50%. Oh, over 50%. That is the probability of X greater than 0.5. Greater than 0.5. If I want to solve that, it means I'm actually going to make use of a beta distribution to do that. Now, I'm going to show you now the beta distribution, okay, is actually f of s equal x raised to the power p minus 1, 1 minus x raised to the power q minus 1, or b of p q. Okay, now your p has been given in this question to be 5, and your q equal to 4. You want to find the probability of s greater than 50%, right? Which is the probability of s greater than 0.5. You're going to go from 0.5 to 1, because you know that the range of x is from 0 to 1. The random variable is a continuum, is a proportion. Now, x, what is that? 5 minus 1. Okay, 4 minus 1. The x divided by b of 5, 4. Look at that. Okay, now this is basically going to be equal. This is going to be the probability of s greater than 0.5, 0.5 to 1, x raised to the power 4, 1 minus x raised to the power 3 dx. Then outside here, the b of 5, 4. I told you about the b of 5, 4 is going to be gamma 5, gamma 4, gamma 5 plus 4. So which is going to be 4 factorial, 3 factorial, 8 factorial. Let me see. 5 minus 1, 4 minus 1, 9 minus 9 factorial, 9 minus 1. Okay, when you get this, okay, that is what you're going to put here. Okay, that's what you're going to, so you're now going to integrate that. If you want to integrate that, you force expand, you integrate that over this range, that will give you your result, but that is going to waste your time. Why not use P better? Okay, if you want to solve this, what I'm just going to do, if I want to solve this in R, instead of using the whole of this, I'm just going to do, they say more than this, 1 minus P beta. Okay, I'm going to indicate 0.5. Then what about shape, which is the values of P, 5, scale, 4, and the lower tail, whatever, this is going to give me results on time. Very easy. Okay, because of that, I provided some example in R. If Y has a beta distribution with 3 and 18, where 3 is the P and 18 is Q, find the probability of Y less than 0.5. This is how to compute that in R. Very easy. For greater than, 1 minus. For between that, very easy to do in R. But if you want to do that manually, there's no problem. Only that, you're going to, if you want to do that manually, you need to revisit your knowledge of calculus. But if you don't want to, if you don't want to revisit your knowledge of calculus, use the software. Very easy. You're going to get your results. This is going to be the end of chapter 6. And when next we're meeting on Monday, it's going to be chapter 8. Over the weekend, I'm going to release the midterm 2 practice questions. The midterm 2 practice question is not going to be cumulative. Everything, I'm going to give you the guide over the weekend. Check the announcement section, what the midterm 2 is actually going to cover. Okay, make sure you stay safe and have a lovely weekend. Those of you online, is there any question? Do you have any question for me?
No, thank you. Have a good day.
You're welcome, and have a good day too.
Thank you.
Okay.